Module 31, Lecture A, Scaling Workloads. By the end of this lecture, you will be able to design out-of-core workflows using batches and incremental estimators, use hashing, sparse matrices, and incremental preprocessing to reduce memory pressure, and measure prediction latency and throughput for fitted models. Out of core. Streaming data batches. Streaming data in batches lets systems process datasets that are too large to fit in memory. Instead of loading everything at once, data such as logs or sensor readings is handled in smaller portions. Each batch must be sized to keep processing efficient while avoiding memory overload, which requires careful planning of storage and processing. A streaming batch workflow processes large sequential data sources, such as files or database cursors, one batch at a time. Each batch is fetched, transformed, used to update results, and then cleared from memory before the next batch begins. This keeps memory use low and improves reliability, because processing can resume from the last completed batch instead of starting over after an interruption. Batch size affects memory use, speed, and reliability. Smaller batches use less memory but may run slower, while larger batches can improve throughput but increase the risk of crashes. Start with a cautious size, monitor performance, and adjust as needed, while keeping processing consistent and using validation and logging to catch problems. Python code. Streaming data batches. Stream data in batches through an incremental classifier, updating the model once for each batch. This shows how batch-based learning can track progress while using memory efficiently. We import NumPy for numerical work and Scikit-Learn for machine learning tools. From Scikit-Learn, we use a dataset generator for classification, a stochastic gradient descent classifier, an accuracy measure, and a train test splitting tool. Together, these imports provide what we need to create data, train a model, and evaluate its performance. We create a synthetic classification dataset with Scikit-Learn containing 3,000 samples and 12 features. 8 features are informative, while 2 are redundant combinations of the informative ones. A fixed random state of 42 makes the dataset reproducible for testing and debugging. We split the dataset into training and testing sets using Scikit-Learn's train test split function. A quarter of the data is kept for testing, while stratification preserves the original class balance and a fixed random state makes the split reproducible. This lets us train on one portion of the data and evaluate performance on unseen data to judge how well the model generalizes. Before streaming begins, the code verifies that the training features and labels have the same count. This confirms that every feature set has a matching label. If they do not align, it raises an error, so the data can be fixed before training continues. The setup uses batches of 250 samples and defines 2 class labels, 0 and 1, for binary classification. It then creates a Scikit-Learn stochastic gradient descent classifier configured for logistic regression. The model is set to update one batch at a time without early stopping, and a fixed random seed ensures reproducible results. The process begins by setting a batch counter to 0, then looping through the training data using the chosen batch size. Each loop selects a valid slice of features and labels without going past the end of the dataset. This lets the model train on smaller batches and update incrementally in an efficient way. The model is updated in small batches using the partial fit method, which adjusts its parameters from the latest features and labels. This makes the approach useful for streaming data or very large datasets. After each batch is processed, a counter is increased to track progress. The trained classifier predicts labels for the test data to show how well it performs on examples it has not seen before. An accuracy score then compares these predictions with the true test labels and reports the proportion that were correct. The output summarizes key details from the training run: the Scikit-Learn version for reproducibility, the number of stream training rows, the batch size, the number of model updates, and the largest batch shape. It also reports the held-out accuracy, rounded to 3 decimal places, giving a quick measure of performance on unseen data. This script shows how to train an incremental classifier by streaming training data in small batches. It creates a synthetic dataset, splits it into training and test sets, and updates a stochastic gradient descent model one batch at a time to reduce memory use. After all batches are processed, it evaluates the model on held-out test data and reports key run details, including batch information and final accuracy. This approach is useful when working with datasets too large to load into memory at once. Incremental model updates. Incremental model updates support out-of-core learning by training on small batches instead of loading an entire dataset into memory. After each batch, the model updates its parameters and keeps what it has learned so far. This is useful for very large or continuously arriving data, such as in fraud detection or recommendation systems, allowing the model to improve steadily over time. For incremental updates, choose data batches carefully by considering their order, size, and quality. If the data has a natural order, make batches representative or shuffle them to avoid biased early training. Use a batch size that balances stable updates with memory limits, speed, and update timing. Validate regularly to catch errors, inconsistent data, and model drift. Incremental updates let a model learn from new data without retraining from scratch, which is useful for large or continuously growing datasets. To use them reliably in production, save the model's current state and track which batches have already been processed, so training can resume after interruptions. This works best when the estimator supports meaningful updates and the data stream stays stable, helping avoid accumulated errors. Python code, incremental model updates. This example trains a model in small batches, updating it incrementally instead of loading all the training data at once. Tracking accuracy after each batch shows how the model gradually improves as it learns. We import NumPy for numerical work and Scikit-Learn tools for building and evaluating a classification model. These tools generate a synthetic classification dataset, split it into training and testing sets, standardize the features, train a stochastic gradient descent classifier, and measure performance using accuracy. We create a synthetic classification dataset using Scikit-Learn's make classification function. It contains 3,000 samples with 12 features, including 8 informative features and 2 redundant ones. A fixed random state ensures the same dataset is generated each time, giving a controlled setup for testing how well a model learns from data. We split the dataset into training and testing sets, so the model is evaluated on data it has not seen during training. Using Scikit-Learn's train-test split function, we reserve 25% of the data for testing. Stratifying by the labels keeps the class balance the same in both sets, and setting a random state makes the split reproducible. Before training, the code verifies that the number of feature rows matches the number of labels. This ensures every training example has a corresponding label, which is required for supervised learning. If the counts do not match, it raises an error so the data can be fixed before training begins. To make training batches more representative, the data is shuffled in a reproducible way using a fixed random seed. A random ordering is applied to both the training features and their labels, so each example stays matched with its correct label. This helps create more diverse, less biased batches for incremental model training. The setup uses an incremental standard scaler, so each incoming batch is normalized consistently. It then creates a stochastic gradient descent classifier with logistic loss for binary classification, updating the model one batch at a time instead of fully converging on each pass. Early stopping is disabled, and the two possible classes are defined as 0 and 1, so the model can learn the binary task incrementally. Set the batch size to 300, so the model processes that many samples per update. Then, prepare two tracking lists, one for the number of batches processed and one for the model's accuracy after each batch. This lets you update the model step by step while monitoring its performance over time. The training data is processed in batches by looping through the samples in steps of the batch size. For each batch, the stopping point is limited, so it does not go past the end of the dataset. The corresponding features and labels are then selected, allowing the model to handle the data incrementally, one batch at a time. The scaler first learns from each new batch of features, then standardizes that batch using the updated scaling information. The model is then trained on the scaled features and their labels, allowing it to improve incrementally as more batches arrive. Providing the full set of possible classes ensures the model understands all output categories during training. The test features are first scaled using the same settings learned from the training data, so both datasets are comparable. The trained model then predicts labels for the scaled test samples. Finally, accuracy is measured by comparing those predictions with the true labels, showing how well the model performs on unseen data. The code records training progress after each batch. It adds the next batch number to a tracking list, then stores the current accuracy so the model's performance can be monitored over time. The output summarizes an incremental Scikit-Learn training run by reporting the library version, the total number of processed batches, and the final test accuracy rounded to 3 decimal places. It also compares accuracy from the first 3 and last 3 batches, giving a quick view of early learning progress and performance near the end of training. This script shows incremental training with a stochastic gradient descent classifier on a synthetic classification dataset. It splits the data so the test set stays unseen, then processes the training data in shuffled batches while updating both the scaler and the model. After each batch, it checks test accuracy, showing how performance improves as learning progresses. The output summarizes the Scikit-Learn version, number of batches, final accuracy, and early versus late accuracy results. Mini-batch training. Mini-batch training handles large datasets by training on small groups of records at a time and updating the model after each group. It is more efficient than using one record at a time and avoids the memory demands of loading all data at once. This keeps training steady and memory use predictable, while allowing data to remain on disk or in cloud storage. Mini batch size affects memory use, training speed, and the stability of model updates. Smaller batches use less memory, but can make updates noisier, while larger batches can train more efficiently, but may exceed memory limits. The best choice depends on the data size, feature complexity, available memory, and preprocessing cost. So the goal is to balance reliable learning with efficient computation. In mini-batch training, how batches are formed and ordered can strongly affect learning. Sequential data may bias the model toward recent patterns, so batches often need to be shuffled or drawn from multiple sources to better represent the full data distribution. In some cases, such as fraud detection, preserving time order is important so the model can adapt to change. A good mini-batch process manages data efficiently while helping the model learn reliably at scale. Python code. Mini-batch training. Mini-batches let models train on small portions of data instead of loading everything at once. Incremental estimators learn by updating after each batch, and tracking accuracy over repeated batches shows how the model improves over time. We import key tools for building and evaluating a simple machine learning workflow. NumPy supports efficient numerical work, while Scikit-Learn provides tools to create a synthetic classification dataset split it into training and test sets, scale the features, train an SGD classifier, and measure accuracy. Feature scaling is especially important because stochastic gradient descent models are sensitive to differences in feature size. We create a synthetic classification dataset with Scikit-Learn to test model training efficiently. It contains 4,000 samples with 12 features, 8 of which are informative and the rest noise. A fixed random state ensures the data can be reproduced, making this a manageable stand-in for a larger dataset. We split the dataset into training and testing parts, so the model is evaluated on data it has not seen during training. Using Scikit-Learn's train-test split, we reserve 25% of the data for testing. Stratification keeps the class proportions balanced, and a fixed random state makes the split reproducible. Before incremental training begins, the code verifies that the training features and labels have the same number of rows. This confirms that every feature set has a matching label. If they do not align, it raises an error to prevent supervised training from running on invalid data. We use a batch size of 250, so training processes that many samples at a time. A standard scaler then updates its estimates of the data's mean and variance one mini batch at a time, which makes scaling more efficient for large datasets. The training features are processed in mini batches based on the chosen batch size. For each batch, the scaler updates its statistics using the partial fit method. This lets the scaler learn incrementally from smaller slices of data, instead of needing the full dataset at once. We set up a stochastic gradient descent classifier using log loss, which is appropriate for classification and log likelihood optimization. The model is configured for one training pass at a time, so it can learn from mini batches, with early stopping disabled to keep manual control over training. We also set a random seed for reproducible results, identify all possible training classes, and prepare a list to record accuracy after each mini batch. The training data is processed in mini batches, with each batch scaled before being used to update the model incrementally through the partial fit method. The matching labels and known classes are provided during each update. After every update, the test set is scaled in the same way. Predictions are made, and accuracy is recorded to track performance over time. The output summarizes key training details for a mini batch process. It reports the Scikit-Learn version for reproducibility, the mini batch size, and the total number of batches used. It also compares accuracy after the first and last mini batch to show how the model's performance changed during training. This script shows how to train a stochastic gradient descent classifier with mini batches. It creates a synthetic dataset, splits it into training and test data, then scales and trains the model incrementally in batches. After each batch, it checks test accuracy to track how performance changes over time. The final output reports basic run details, including the Scikit-Learn version, batch size, number of batches, and the first and final accuracy scores. Memory-efficient features. Feature hashing. Feature hashing turns very large or changing sets of features into a fixed-size numeric representation. It uses a hash function to map feature names into a limited number of columns, avoiding the need to store an ever-growing dictionary. This keeps memory use low and makes processing more predictable for large-scale or streaming tasks, such as text classification and fraud detection. Feature hashing helps handle changing or unknown categories without storing a full feature dictionary. It keeps model inputs consistent across batches while reducing memory use for both the data matrix and related metadata. This makes it useful for large, frequently updated datasets. Feature hashing saves memory by mapping many possible features into a fixed size space. But this can cause collisions when different features share the same position. This is often acceptable for sparse data such as text or logs if the hashed space is large enough. The main choice is balancing memory use against collision risk, and sparse storage helps keep the approach scalable while preserving good prediction accuracy. Python code. Feature hashing. Feature hashing creates compact, sparse features without storing an ever-growing vocabulary dictionary. It maps inputs into a fixed-size representation, making it useful when the set of possible features is large or changing. The output compares this hashed representation with a traditional vocabulary-based approach. These imports prepare the tools needed for feature transformation in machine learning. NumPy supports numerical work with arrays and matrices, while Scikit-Learn provides machine learning utilities. The feature hasher converts data into fixed-size feature vectors, and the dictionary vectorizer turns feature mappings into matrix form while learning the feature names. A small collection of events is represented as dictionaries, where each event contains categorical features such as a word, merchant, or device, marked with a value of 1. This structured format shows how event attributes can be prepared for conversion into numerical features for machine learning. The specific feature choices are arbitrary and are used only to illustrate the representation. Scikit-Learn's dictionary vectorizer converts event dictionaries into a numerical matrix for analysis or modeling. It learns the unique feature names in the data and creates one column for each feature. Using a sparse output format helps store this matrix efficiently, especially when the dataset may be large. Scikit-Learn's feature hasher converts event dictionaries into a compact, fixed-size matrix. Setting 8 features makes every output have 8 columns without needing to fit a vocabulary first. Because the input is dictionary-based and alternate signs are disabled, the transform values are positive and efficiently represent the original data. First, verify that the vocabulary matrix has the same number of rows as there are events, so each event has exactly one matching row. If the counts differ, raise an error to signal an unexpected matrix shape. This check confirms that the transformation preserved the data's required structure. The validation checks that the hashed matrix has one row for each event. If the counts do not match, it raises an error for an unexpected row count. This confirms that the transformation preserved the data's expected structure. We first collect the feature names learned from the events, then test how each one is handled by the feature hasher. Each feature is transformed on its own, so we can see which hashed column it maps to. By checking the non-zero positions in the resulting matrix, we can understand how features are distributed across the fixed columns and spot possible collisions when different names land in the same column. We use NumPy to count the distinct hashed feature columns, which shows how many unique columns remain after hashing. Then we compare this count with the original number of feature names to find how many names collided by mapping to the same hashed column. The output checks the Scikit-Learn version for reproducibility, then compares 2 feature representations. The vocabulary-based matrix shows how many events and learned unique features were captured, while the hashed matrix has the same events but a fixed number of columns set by the feature hasher. It also reports that the vocabulary method stores feature names, whereas hashing does not, and summarizes the hashed matrix by counting non-zero values and collisions. These collisions show the trade-off between using a small fixed hash space and the risk of different features sharing the same column. This script compares traditional vocabulary-based encoding with feature hashing for categorical event data. A dictionary vectorizer stores every unique feature name and creates a sparse matrix based on that vocabulary, while a feature hasher produces a fixed-size sparse matrix without storing feature names. The script verifies that both methods keep one row per event. then checks how many original features land in each hashed column to detect collisions. Overall, it shows the trade-off between lower memory use and the risk that different features may share the same hashed column. Incremental pre-processing. Incremental pre-processing handles data in small batches instead of loading it all into memory at once. This is important for large-scale machine learning, limited memory systems, and continuous data streams. Each batch is processed, useful information is kept for later steps, and unnecessary data is discarded, allowing pre-processing to work as an efficient streaming workflow. Incremental pre-processing helps scale large datasets without loading everything into memory. It updates summaries batch by batch, such as averages, ranges, token counts, or sparse representations, so features stay useful for learning. This keeps the important information needed by the model while reducing unnecessary data handling. Incremental pre-processing must keep transformations consistent across data batches, so the model is not misled by artificial differences. Scaling, encoding, and similar steps should use stable parameters, applied uniformly, especially in production systems, where new data must match the training feature space. This approach saves memory, supports continuous data flow, and helps large-scale learning remain both statistically reliable and operationally stable. Python code, incremental pre-processing. This example shows how to scale data in small batches to avoid making full copies of the dataset. It compares the memory use and scaling results of this incremental pre-processing approach. We import NumPy for numerical work and Scikit-Learn for machine learning tools. From Scikit-Learn, we use the standard scaler, which standardizes features by removing the mean and scaling them to unit variance. This helps many machine learning algorithms perform more effectively. We simulate data arriving in batches to reflect streaming or incremental loading. A fixed random seed makes the results reproducible. And the dataset contains 6,000 rows with 4 features each. Processing 1,000 rows at a time keeps memory use manageable and supports efficient handling of larger datasets. The process creates data in smaller batches instead of all at once. A loop generates each batch with random normal values using a mean of 50 and a standard deviation of 10, then stores it as 32-bit floating point data. Each batch is added to a collection, which helps manage memory efficiently when working with large datasets. Create a standard scaler to learn the data's mean and variance in batches, which is useful when the full dataset is too large for memory. As each batch is processed, the scaler's partial fit method updates these statistics incrementally. This allows the data to be scaled efficiently without loading everything at once. To compare incremental pre-processing with processing the full dataset at once, all batches are combined into one complete array. A standard scaler is then fit to this full data, so it can learn the overall mean and variance. This full dataset approach serves as a baseline for evaluating how incremental scaling differs in memory use and results. We take the first data batch as an example and apply the incremental scalar's transform method to it. The scaler uses the global statistics learned from earlier batches to standardize the new data. This produces a scaled batch where each feature is adjusted toward a mean of 0 and a standard deviation of 1. The code compares memory use for the full dataset and for a single batch, showing the benefit of processing data in smaller chunks. It then measures the largest difference between the averages learned by the incremental scaler and the full scaler. This confirms how closely the incremental method matches the full dataset statistics. Check that the scaled batch has the same shape as the new batch to confirm the transformation did not change the data dimensions. If the shapes differ, raise an error because scaled data should preserve the original input structure. This verifies that the incremental scaler learns statistics compatible with the data. The output summarizes key checks for incremental scaling. It reports the Scikit-Learn version, the number of rows and batch size, and compares memory use for the full dataset versus one batch. It also shows the largest difference between incremental and full dataset scaling means, helping confirm that batch processing closely matches the full approach. It includes a quick check of the scaled batch's first row. This script shows how to scale large datasets incrementally by processing small batches instead of loading everything into memory. An incremental scaler learns the data's mean and variance batch by batch, then uses those learned statistics to transform new data. The results are compared with a standard full dataset scaler to check accuracy, including the difference in learned means. The script also highlights the memory savings of using one batch at a time and confirms that the scaled output keeps the same shape as the input. Sparse feature storage saves memory by keeping only non-zero active features instead of allocating space for every possible feature. This is especially useful in high-dimensional tasks like text classification and online advertising, where each instance uses only a small fraction of available features. As a result, systems can process larger datasets within limited memory. Sparse storage saves memory by keeping only the features that are actually active and their values. This is especially useful in large feature spaces from methods like feature hashing or one-hot encoding, where most possible features are inactive for each example. By storing only the active entries, systems can hold more data in memory, move less data, and train models efficiently on limited hardware without losing important information. When using sparse feature storage, choose models and pre-processing steps that preserve sparsity. Some methods can turn sparse data into dense data, which increases memory use and reduces efficiency. Careful scaling and normalization help keep zeros unchanged, improving training speed and deployment performance in large machine learning systems. Python code. Sparse feature storage. Dense storage records every feature value, while sparse storage keeps only the values that are active. Sparse storage is most useful when the data contains many zeros, because it can greatly reduce memory use. We import NumPy for efficient numerical work with arrays, and use Scikit-Learn's feature hasher to convert categorical data into hashed features. This is useful for representing high-dimensional data without storing every feature name explicitly. The data is represented as a collection of rows, where each row stores only the categorical features that are active, such as a city, device type, or ad category. Each active feature is marked with a value of 1. This creates a simple example of sparse data, where most possible features are absent from each row, making it useful for demonstrating sparse feature storage. Scikit-Learn's feature hasher efficiently encodes categorical data by mapping dictionary-based records into a fixed-size sparse matrix with 1024 columns. It avoids storing feature names and keeps only active features, which helps reduce memory use. This makes it useful for high-dimensional categorical data with many possible categories. The code converts a sparse matrix into a dense array using the matrix object's dense conversion method. In the dense form, memory is reserved for every entry, including zeros, unlike the sparse form, which stores only non-zero values. This can be useful for operations that require a dense matrix, but it uses more memory. Before comparing memory use, first confirm that the sparse and dense matrices have the same shape. This ensures they represent the same data structure. If the shapes differ, an error should be raised so the issue can be fixed before making the comparison. To compare memory use, estimate the sparse matrix size by adding the storage for its data, indices, and index pointers. Then compare this with the dense matrix size, which is simply the memory needed for the full array. This shows how much memory sparse storage can save. 2. Measure how much of a sparse matrix is active. First, find the total number of cells by multiplying its rows by its columns. Then count the cells with non-zero values. Dividing the non-zero count by the total cell count and multiplying by 100 gives the percentage of the matrix that is actively used. This section explains how sparse feature storage is used for hashed categorical indicators. It summarizes the sparse matrix size, the number and percentage of active non-zero cells, and then compares dense versus sparse memory use. The key takeaway is how much more memory the dense representation requires, showing the efficiency gained from storing only active features. This script compares sparse and dense storage for hashed categorical features. It turns records such as city and device type into a sparse feature matrix, then converts it to a dense version with the same shape for comparison. The key result is that sparse storage keeps only non-zero entries, while dense storage reserves space for every possible value, including zeros. By reporting the matrix size, active cells, and memory use, the script shows why sparse representation is much more efficient for data with many zeros. Prediction performance. Memory-mapped models. Memory-mapped models make large fitted models more efficient by loading only the parts that are actually used into RAM. This reduces startup time and memory use, especially for models with very large parameter arrays. When several worker processes use the same read-only model, the operating system can share those memory pages, allowing services to handle more requests on the same hardware. Memory-mapped models work best when predictions repeatedly use the same parts of the model, because the operating system can cache those parts and make later predictions faster. They may feel slow at first, then improve as the cache fills. But if access is scattered, especially on slower storage, some predictions can become much slower. For interactive systems, it is important to measure not only average speed, but also these occasional latency spikes. Memory-mapped models are best deployed as fixed, read-only files that prediction workers share. This reduces data copying, lets the operating system manage memory efficiently, and keeps training separate from serving. Teams may pre-warm services and compare cold start with warm cache performance. But the main benefit is better scalability by matching model access patterns to system memory management. Python code, memory-mapped models. This example compares standard prediction with memory-mapped prediction. Memory mapping can share large fitted arrays, and the comparison focuses on latency and throughput after the model is loaded. We import NumPy for numerical work, including arrays and math operations, and use Scikit-Learn for machine learning tools. From Scikit-Learn, we use a dataset generator to create synthetic classification data and logistic regression to build a model for binary classification. We create a reproducible synthetic classification dataset using Scikit-Learn's make classification function. It contains 3,000 samples with 20 features, and a fixed random state ensures the same data is generated each time. This makes it useful for consistently testing and comparing models. We create a logistic regression model in Scikit-Learn, setting a maximum of 300 iterations and a fixed random state for reproducible results. The model is then trained on the features and target values, learning coefficients that help separate the classes and prepare it for prediction. The fitted logistic regression coefficients are converted to a precise floating point format, then stored in a memory-mapped array on disk. This array has the same shape as the original coefficients and can be written to and read from later. Using memory mapping helps handle large data efficiently without keeping everything in memory, which is useful when memory is limited or data must be shared between processes. Copy the fitted model's coefficients into the memory-mapped array so they can be accessed efficiently later. Then, use the flush method to write the changes to the underlying file, making the stored data persistent and ready for future use. We reopen the memory-mapped file of model coefficients in read-only mode using NumPy's memory mapping. The file is read with the same float64 data type and the original array shape, so the coefficients can be accessed like a normal NumPy array without risking accidental changes. Before continuing, the mapped coefficients are checked against the fitted model's original coefficients. A NumPy approximate equality check confirms that the two arrays match within tolerance. If they do not, an error is raised, helping ensure the stored data is valid before further computation. A batch is prepared by taking the first 500 feature rows and converting them to a floating point format. The prediction process is then repeated 80 times to evaluate performance and consistency across multiple runs. The code measures how long repeated predictions take using ordinary model coefficients. It records the start time in nanoseconds, runs the prediction calculation several times by multiplying the feature batch by the transposed coefficients and adding the intercept, then records the end time. The difference gives the total elapsed time for the repeated predictions. The process measures prediction time by recording the current time before and after repeated prediction runs. In each run, it computes scores by multiplying the feature batch by the transposed memory-mapped coefficients and adding the model intercept. The difference between the two timestamps gives the total time spent making predictions with the memory-mapped coefficients. The code converts elapsed prediction times from nanoseconds to seconds for both normal and memory-mapped predictions, making the timing easier to interpret. It also calculates the total number of predictions by multiplying the batch size by the number of repeats. Together, these values help assess prediction throughput and latency. The performance metrics compare normal and memory-mapped coefficients. Latency is found by converting elapsed time to milliseconds and averaging it over the repeats, giving the average time per batch. Throughput is found by dividing the total predictions by elapsed time, giving predictions per second for each approach. The prediction scores from both the normal and memory-mapped coefficients are converted into binary class labels by checking whether each score is at least 0. These two label sets are then compared to confirm they match exactly. If they differ, an error is raised, showing that the memory-mapped method does not reproduce the normal prediction results. The output reports the Scikit-Learn version for reproducibility, then compares prediction performance using standard coefficients and memory-mapped coefficients. It shows the batch size, latency per batch, and throughput for both methods. Finally, it verifies that both approaches produce matching predictions, confirming that memory mapping preserves correctness. This script shows how memory-mapped arrays can improve prediction efficiency for a logistic regression model. It trains the model on synthetic classification data, stores the learned coefficients in a memory-mapped file, and compares predictions made with standard coefficients versus memory-mapped ones. Both approaches produce the same predictions, confirming correctness, while the script reports latency per batch and throughput in predictions per second. The main takeaway is that memory mapping can help machine learning workflows handle large data or limited memory more efficiently. Latency measurement. Latency measures how quickly a model returns a prediction after receiving input, which directly affects user experience in time-sensitive applications. It includes the full request-to-response process, not just the model's computation. So validation, pre-processing, and other preparation steps matter. A model that seems fast in isolation can still be slow in practice if the surrounding workflow is inefficient. Latency measurements should match how the model is actually used. For single request use, run timing tests repeatedly because prediction time can vary due to scheduling and memory effects. Distinguish cold latency, the first prediction after loading, from warm latency during normal operation. Also examine high percentile latency, not just averages, to capture slower responses. Interpret latency in terms of what the application requires, since some models need millisecond responses, while others can tolerate delays. If latency is too high, first look at pre-processing, feature reuse, and keeping models in memory before simplifying the model. Measure performance on hardware similar to deployment, so teams can balance accuracy, speed, resource use, and user experience. Python code latency measurement. Measure how quickly a fitted model makes predictions by testing both single requests and small batches. Report the results in milliseconds and in predictions per second to compare latency and throughput. We import the main tools needed to build a simple classification workflow: NumPy for numerical work, Scikit-Learn for machine learning, and the breast cancer dataset for practice. We also use logistic regression as the classifier, split the data into training and testing sets to evaluate performance, and combine pre-processing with modeling in a pipeline. A standard scaler normalizes the features, so differences in scale do not distort model training. We load the built-in breast cancer classification dataset from Scikit-Learn and separate it into input features and target labels. The features describe each example, while the target gives the label the model will learn to predict. This prepares the data for training and evaluating a machine learning model. The code verifies that the feature data has the same number of rows as the target labels, so every example has a matching label. If the counts differ, it raises an error to stop training or evaluation before a mismatch causes problems. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function, with 1/4 of the data kept for testing. Stratification preserves the original class balance in both sets, supporting fair evaluation. A fixed random state of 42 makes the split reproducible each time the code runs. A machine learning pipeline is built to pre-process the data and train a model. It first standardizes the features so they are on a common scale, then applies logistic regression with settings that support reliable training and reproducible results. The pipeline is fitted to the training features and labels so the model can learn patterns in the data. To prepare for latency testing, we choose one test example for a single prediction and 32 examples for a batch prediction. We run both predictions once to warm up the model and reduce any startup overhead. This helps make later timing measurements more consistent and reliable. To measure prediction latency, we use NumPy's timing tools, so no extra libraries are needed. The timing is repeated 80 times to make the results more reliable, and each single request latency is stored in milliseconds. These recorded values can then be used to calculate summary statistics, such as the median and percentile latencies. A loop runs for the chosen repeat count to measure how long single data point predictions take. For each run, it records the time before and after calling the model predict method, then converts the difference from nanoseconds to milliseconds. Each measured latency is stored as a floating point value in a list for later analysis. To measure batch prediction latency, we repeatedly time how long the model takes to process the same batch request. For each run, we record the start and end time in nanoseconds, convert the elapsed duration to milliseconds, and store it as a number in a latency list. These collected measurements can then be analyzed to evaluate the model's prediction performance. We use NumPy's percentile calculation to summarize prediction latency. The median shows the typical response time for single predictions, while the 95th percentile highlights slower cases that most predictions still beat. We also calculate the median latency for batch predictions to compare typical batch performance with single request performance. To convert batch latency into throughput, first identify the batch size, or how many samples are processed in one request. Then divide that batch size by the median latency converted to seconds. The result is the number of predictions per second, showing how efficiently the model handles batched data. The output reports key performance details for the model. It shows the Scikit-Learn version for reproducibility, then summarizes prediction latency using the median and 95th percentile for single requests. It also reports median batch latency and throughput, showing how efficiently the model handles multiple predictions at once. This script benchmarks how quickly a logistic regression model makes predictions on the breast cancer dataset. After training the model with pre-processing, it warms up prediction calls, then measures repeated single predictions and small batch predictions. It reports median and 95th percentile latency for single predictions, plus median batch latency converted into predictions per second. The output also includes the Scikit-Learn version, giving a concise view of the model's prediction speed and efficiency. Throughput measurement. Throughput measures how many predictions a model can produce over time, not how fast one prediction is made. It matters when systems must handle large volumes of data, such as processing transactions or updating recommendations. A good measurement should use realistic inputs and include pre-processing and data handling, so it reflects the system's true capacity under real-world conditions. Throughput depends on whether a model makes single predictions or processes batches. Batching often improves efficiency by reusing model parameters and taking advantage of vectorized operations and hardware such as GPUs. But batches that are too large can overload memory and slow results, so the goal is to choose a batch size that keeps prediction rates high without straining resources. Throughput should be measured in conditions that match the model's real deployment environment, including hardware, concurrency, disk speed, network transfer, and shared resources. Warm tests show steady-state performance, while cold tests include startup costs that matter for scaling and recovery. These measurements help guide choices about batch size, hardware, and deployment strategy, so the model can handle real workloads effectively. Python code. Throughput measurement. Measure prediction throughput by checking how many predictions a fitted model can make per second. Changing the batch size affects this rate, and larger batches can show faster processing. We import key Python tools for a basic machine learning workflow. NumPy supports efficient numerical work, while Scikit-Learn provides tools to create synthetic classification data, build a logistic regression classifier, split data into training and testing sets, and standardize features so they have zero mean and unit variance. We create a synthetic classification dataset using Scikit-Learn's make classification function. It contains 6,000 samples with 20 features, and a fixed random state makes the data reproducible. This gives a consistent dataset for testing and comparing model performance. We split the dataset into training and testing sets using Scikit-Learn's train-test-split function. 40% of the data is reserved for testing, so the model can be evaluated on unseen examples. Stratifying by the target keeps class proportions consistent across both sets, and setting a random state makes the split reproducible. A standard scaler is used to normalize feature data, so each feature is on a comparable scale for learning. It is fitted only on the training data to learn the mean and standard deviation, then used to standardize the training features. The same learn scaling is applied to the test features, keeping training and test data consistent for evaluation. We create a logistic regression model for classification, allowing up to 300 iterations so it can converge. A fixed random state makes the results reproducible. The model is then trained on the scaled training features and target values, learning the patterns needed to make predictions on new data. The code first checks that the test set has at least 1,000 rows, so throughput measurements are based on enough data to be meaningful. If the test set is smaller, it raises an error explaining that more rows are required. This validation helps keep the measurement results reliable. Before measuring prediction throughput, the model is warmed up by running predictions on the first 100 test samples. This helps the model reach a steady operating state, making the later timing measurements more accurate. The setup defines several batch sizes, from 1 to 1,000, to measure how many predictions can be made at once. It also prints the Scikit-Learn version for reproducibility, then prepares a simple results header showing batch size and predictions per second. The process measures model prediction throughput for different batch sizes. For each batch size, it selects a matching test batch, repeats prediction enough times to get a stable timing, and records the total elapsed time. It then calculates how many predictions were completed per second and prints that throughput for each batch size. The code performs a final check on the last batch by counting how many predictions were produced. It reports this count to confirm that the model generated the expected number of output labels for the input batch. This script tests how quickly a trained logistic regression model can make predictions at different batch sizes. It creates and scales a synthetic classification dataset, trains the model, then measures predictions per second for batches of 1, 10, 100, and 1,000 samples. By repeating each test enough times, it shows that larger batches generally improve throughput, highlighting the efficiency of batch processing. It also checks that the final batch returns the expected number of predictions. In this lecture, you learn to design out-of-core workflows using batches and incremental estimators, use hashing, sparse matrices, and incremental preprocessing to reduce memory pressure, and measure prediction latency and throughput for fitted models. In the next lecture, Lecture B, we will go over parallel configuration.
Thank you for your attention. See you all in the next lecture.